The same idea is true here like we had in our circle graphs where I could actually plug in values, like plug in my theta and calculate a bunch of coordinates. But again, it's more about design than having to do 10, 15 coordinates. But for example, let's say I put in pi over 3. Okay, well the cosine of pi over 3 is 1/2. 3 times a half, 3 halves. 3 plus 3 halves, 4.5. Now if you check it out, again, I freehand drew this, but on the rotation line, pi over 3, counting out 1, 2, 3, 4.5 would put me about right there. So, pretty darn close, right? Again, we could do that, but we don't because, you don't need to. Just those points will do. So it's all about related distances. And once you get that relationship down, cardioids are a piece of cake. Now, there is the distinction, right? Which one do I have? So let's go through the dimple and the interior loop. How you know it's a dimple is first number bigger than second number. The axis idea is still there, so with a positive 3 sign, I can tell you right now I'm visualizing my cardioid sitting up here. What you won't have in a dimple is you won't have an origin point. But let's start out with the lobes. First number is still the lobe, so 1, 2, 3, 4, 1, 2, 3, 4. Add them together, 4 plus 3 is 7, takes you out to the large part of the heart. Then what you do to get the dimple, or the distance off the origin, is you subtract the 2. So 4 minus 3 is 1. So first number 4, and 4 to the lobes, 4 plus 3 to the large part, 4 minus 3 on the opposite side of the origin to the dimple. And then again, go ahead and draw it. Okay, why don't you guys try the second one on your own now that we've done a few together. So always start out with cosine or sine, positive, negative, what axis is the cardioid sitting around, and then do your distances. I'll give you guys a second just to kind of walk through it here. Okay, number one, negative 4 cosine. So right now I'm visualizing sitting around the negative x-axis. Again, no origin point with a dimple. 6 be my first number, so 6 and 6. Add them together, 6 plus 4 is 10. That's going to put you way out there. 6 minus 4 is 2. And there you go. Okay, so we're going to go on to the interior loop, and basically it's the same idea, right? With a little exception of how do you get the loop. What's nice about these 3 styles of graphs is most of what you're doing is really the same thing. Okay, negative 4 sine. So here we go. Now again, how do I know it's an interior loop? Because first number is smaller than second number. Negative 4 sine means right away I'm visualizing the graph sitting here. These do have an origin point. First number to the lobes. Add them together. Large part of the heart. Oops, that'd be 6 though right there. And then the interior loop is the difference of the two numbers. Now, we're not concerned about positive or negative. It's a distance idea, so like an absolute value idea. So 4 minus 2, negative 2, but really it's just the distance of 2. And again, I'm visualizing this here because reminder that I know that the heart sits here, so the interior loop would have to be here. Again, once that's all in, just go ahead and sketch. It's the same kind of sketching you're doing in the other graphs. Okay, again, I'll give you guys a second to try the next one on your own. Copy it into your note sheet. Same start though, right? Begin with what axis are you around? And then after that, it's just a bunch of counting your distances. Pretty simple. Cardioids are, right? Like they all are actually, again, just getting the design down. Okay, positive cosine. I'm visualizing here. Origin point, first number to the lobes. Let's try that again. There we go. 5 plus 3 is 8. This one only goes out to 7. 5 minus 3, 3 minus 5, but it's a distance of 2. Draw it. Okay, so that's all the cardioids. Next group of graphs we're going to go to is the lemniscate. Lemniscate, rhymes with figure eight. So lemniscate, figure eight, sure is great, however you want to think about it. All right, so the figure eight graphs also probably your easiest graphs. Well, circles are pretty easy too, but there's only a couple little details we got to know. There's the cardioid summary. How do I know which one? The two numbers are the same. Cardioid, lobes to the origin. Dimple, first number bigger than second number. Loop, first number smaller than second number. Okay, let's go to lemniscates. Lemniscates are your only r squared equations. So if you have a list of equations and you're going down from one to the next, going, okay, what am I looking at? R squared, automatic lemniscate. Also, there's some pretty simple design ideas here. All the sine lemniscates have their petals on the pi/4 rotation line. All the cosines are on the x-axis. So kind of a nice little simple note, something to add to your notes. It's kind of a reminder. Those two ideas. There's never any other variation of a lemniscate. So basically sine on the pi/4 rotation line, cosine on the horizontal or the x-axis. Then the other thing that I need to know is how long are the loops, or where the tip of the loop is, because that's basically there'll be an origin point. So you'll plot an origin point, and then there'll be the tips of the loops. So I need to know loop length. How do I get out there? And pretty simple. That's going to be on my next slide, but you guys are probably already there in your notes. Okay, so basically, you know which one we have based on this idea right here. And then loop length is the square root of the a number out front. So if a squared is 9, okay, well then square root of a is 3. So 3 is the loop length. Number 1 is I focus in on which one I have, sine or cosine. Sine petals or loops, are on the pi/4. So on the pi/4 rotation line, origin point. There you go. Now, one other thing to note too about doing this is the circular idea. I'm going to go back a slide for 1 sec while you guys are drawing. Whoops, back a slide. Right out here at the ends of the loops, if you were to draw a line kind of about right there, let's see. This is approximately a semicircle. So once again, the idea of the graphs being very circular, especially lemniscates and cardioids, is important. So again, the idea would be don't go like this and go in real tight, like bow tie, propeller, whatever. Okay, nice big loops. Okay, back to the graphs. So we had the sine idea on the pi/4. I'm going to just put those points back in there quick. Cosine, loops sit on the x-axis, 16, so loop length 4, again, origin point, 1, 2, 3, 4, 1, 2, 3, 4, real simple graph. Okay. Again, as you're doing your sketching, we're thinking circular out here. Okay, that wasn't very good. I might go back and kind of, all right. Okay, lemniscate, figure 8, pretty simple. The last one is the rows, and the rows is actually, there are some things there we can definitely say, like some related ideas, distances, but they don't go as well as like, well, I just have to know a couple things and I can draw them by hand. We really will use the calculator to help us out at least a little bit, because also they don't have there's enough differences in the rows graphs that it's too much to list out and remember all the little differences. You know, with these graphs, like lemniscates, 2 things you got to think of: is it on the pi/4s? Is it on the x-axis based on sine or cosine? Cardioids, again, pretty simple as far as figuring out the stuff. Circles, simple, but rows have a little bit more going on. So there's a few things, and then calculator is going to help take us kind of the part of the way, graphing by hand the rest of the way. First of all, these equations will have a number multiplied by theta. So a number bigger than 1, I should say, so 2, 3, 4, 5, whatever the case is. Different than like a circular graph where that number is just theta. So there's kind of a small distinction. Am I looking at a rose or a circle? Also, what does that number do to the number of petals you have? If that number n is odd, you have that exact number of petals. If it's even, you have twice that many petals. So a 2 theta is 4 petals, a 3 theta is 3 petals, a 4 theta is 8 petals, and so on. One little nice thing to remember, and this is something you guys can put in a note sheet, is that if n is even, the petals are separated by pi divided by whatever n is. If n is odd, the petals are separated by 2 pi divided by whatever n is. Now, here's a list of just kind of in order, the 2s, the 3s, the 4s, the 5s, and so on and so on. And there are definitely some things that are true about these, but the list is so extensive. And as you keep doing this, things kind of get tweaked and changed, that it's just like, okay, all of a sudden it's like roses, there's too much. There's too much to remember, too many things. There's got to be an easier way, which there is. This is a calculator problem. Okay, so what we're going to do is we're going to use the calculator to get a visual going right away. We're going to locate one petal. We're fairly sure, like, yeah, I know where that one petal is. And then basically we're going to talk about the rotational space between petals. And if we need to, we can use our calculator table to help us sort of be sure we're on the right track. And then up here you see some visuals giving you guys some ideas. But if you're looking at this as a group of information, this entire thing, I say, all right, you got to memorize all this to know how to draw rows. It's just too much. And it's not necessary, actually, because, we got the calculator. Okay, let's check out a couple roses. So 4 cosine 2 theta. Now, what I'm going to have you guys do actually right away is go put that into your calculator. I think that actually is the one that I had in there, all right, earlier, so perfect. 4 cosine 2 theta. Now, the thing about this one is there isn't really much to do as far as figuring out where things are at. It's clear the petals sit on the 4-axis, and I know that oh, by the way, sorry, let me go back for 1 sec. How do I know what the length of a petal is? Petal length is the A number, the number out front. So if it's 4, you got the tips of your petals are 4. That also means the tips of the petal would represent a radius 4 if you're tabling and checking that out. By the way, do a whole bunch of stuff to kind of throw at you here quick. You notice here's all the measures doing in pi over 12s. That's typical polar graph paper. Also, I put in all the decimals. You see 1.57, 3.14, the ones you guys know from the past. You don't need to memorize these, so don't panic, don't worry about that. But when you are tabling and you're trying to sort of locate stuff, you kind of got to know what these are, at least be able to count by one rotation line at a time. And I'll explain this in a second to figure out if you're in the right spot. Okay, so back to the calculator for a sec. Like I said, this one requires no real thought because if it's in the calculator, I've got it. The ones where we're going to have to think a little bit more is what about the petals that don't sit on an axis? Like what's their rotation line? What rotation line does the tip of a petal sit on? Okay, I'm going to go back to this one for a sec because, again, easy to draw. Now, here I put in this red kind of dashed line. That does not need to be there. It just kind of gives me a visual of where the tips of my petals at. And again, they're pretty circular out here. I didn't maybe do this one as circular as I could, but don't cut them too short. Okay, so cosine 2 theta, this particular example, fairly simple. It's like I didn't really need the calculator for anything more than a quick visual to get myself oriented with the petals, and I'm good. So that one we're going to go by fairly quick. The last one for the day, a 5 sine 3 theta. So again, I want you to go ahead and put that into your calculator. And then go back to the graph. Now I see a petal sitting clearly on the negative y-axis, and no question about that one. It's not like it's a mystery. That's the one I could draw right away. Going back to my note sheet for a sec. So loop length 5, I can tell you based on what I saw in the calculator, there's a point sitting there. The only question now really becomes is that when you look at the calculator, what rotation line is this petal on? What rotation line is this petal on? It is true that when theta, go back to the note sheet for a sec. When the number in front of theta is odd, the petals have a separation of 2 pi divided by that. So, for example, being this is 3, the petals have a separation of 2 pi over 3. Knowing that, that should actually tell you where these two petals are if you think about it. If the separation between the tips of the petals is 2/3 pi, this one's on the pi over 3 line, this one's on the 2 pi over 3 line. Okay. All right, but we'd like to check it out and see where they really are.